Dear all, everybody can hear me now?
Yes.
Artem, we will start or no?
Yes, of course. Yeah, I'm ready.
Okay, let's start.
So am I right that you will send me as a main here in Zoom so I can record the video?
Yes, you can.
Okay, because I don't have the record button right now.
We record on YouTube now, and
Okay, so
everybody can share screen now too.
Okay, so I can start, right?
Yeah.
Okay. So hello everyone. My name is Artem. Today I will maintain the current session. And yeah, our first speaker now is Minttu, Alakuijala. Minttu, can you please sign that you are ready for the talk?
Yes, I'm ready.
Okay. Yeah, so Minttu is from LJK and Inria laboratories, and today she will present the work about residual reinforcement learning from demonstrations for robot control. So Minttu, the floor is yours.
Thank you, Artem. So, yeah, my name is Minttu Alakuijala, and I'm a PhD student at Inria, ONS, and Google Research. I'm going to be talking about our recent submission called Residual Reinforcement Learning from Demonstrations. This is joint work with Gabriel Julak-Arnold from Google, and my supervisors Julia Meral, Champons, and Cordelia Schmidt. In this work, we propose an approach for combining imitation and reinforcement learning for learning sample-efficient robotic control from data. And a little bit of background for those of you who might not be familiar with reinforcement learning. Typically, we consider the problem of learning to act in an unknown Markov decision process to achieve maximal reward. And a Markov decision process is defined by a set of states S, a set of actions A state transition function, which determines what state you are likely to transition to by taking action AT in state ST. And finally, a reward function, which is what we're trying to maximize. The problem is then to learn parameterized policy by theta that gives an action given at state, such that we maximize the expected discounted return for some discount factor gamma between 0 and 1, which corresponds to this sum here, just the sum of discounted rewards discounted by gamma from time t plus 1 to whichever horizon you're considering. There is more than one way to formulate this, but a very popular one is Q-learning, where you're learning, let's say, a function approximator to estimate this quantity, this expected discounted return, if you're starting from state ST and the first action you take is AT. And we can write this recursively. This should correspond to the immediate reward of the next time step plus the discounted estimate of the Q value at the next state, at the next time step. So here we do a maximization over the action, considering at the future state what would be the best action to take. And this gives us a temporal difference learning update, where we can, again, bootstrap, where we can update the Q function by using bootstrapping with the same function, our own estimate of the Q function. And we should have this temporal consistency that the Q function should correspond to. Now, in residual reinforcement learning, we we want to give a prior to this reinforcement learning agent or the policy. Because even though RL is very general and allows autonomous learning of potentially very hard to specify behaviors, learning from scratch can be very sample inefficient. And especially if we're talking about, if we're interested in real robots, it can be very impractical and even unsafe to explore at random for a long time, starting from scratch. So residual RL has been proposed that allows us to start from a conventional controller. So this could be anything like a PID controller or any control method that you'd like. And we learn to correct it additively using a residual policy, which is trained autonomously using reinforcement learning, such that the resulting output is the sum of both actions. Yeah, this assumes that part of the problem can be efficiently solved by feedback control and that we kind of understand how to solve. And the residual can then kind of learn to correct for model misclassification, sensor noise, or any miscalibration, or kind of some aspects that are hard to model, such as friction. So as this relates to the reinforcement learning problem I presented earlier, it's all it really changes is this the fact that the action that we're applying is not only the action from the current policy, but also from some other base policy. However, this existing works have some drawbacks. First of all, it requires such a hand-engineered controller that can be difficult to provide, and certainly if you're not an expert in robotics. Moreover, these hand-engineered controllers typically require full state. They're operating kind of on full state features. So this includes things like positions of all objects in the scene, or targets or obstacles, and this is what they rely on. Now, where our contribution comes in is we propose to remove this dependency on a hand-engineered controller and provide a prior in the form of demonstrations instead. We will use behavioral cloning on a data set of demonstrations, and we can learn the entire policy from data in this way, using demonstrations for the base controller and autonomous environment interaction for the residual. Moreover, since we're not relying on this classical control, we can use image inputs, we can use deep learning and learn from raw state features such as images directly. And we also show that our method is able to learn the manipulation tasks using only a sparse task completion reward, unlike many other reinforcement learning approaches, which require a dense reward, which requires kind of a reward shaping step. Our method is trained in 2 stages. So first of all, we learn the base controller using behavioral cloning. For this, we have a data set of demonstrated trajectories. We consider a stacked depth or RGB frames, and some proprioceptive inputs that we may have from the robot, such as positions of joints or velocities of joints that we kind of get for free. We train a convolutional neural network to predict the actions that were given in the demonstrations by the expert, which may be a human or it may be any other controller. In the second stage, we fix the base policy and we learn a residual, again with reinforcement learning. It can reuse the bottleneck features from the convolutional neural networks. It doesn't have to learn from scratch the visual, how to use the image. And it also gets as input the base action and proprioceptive features. On top of this, we train a lightweight policy network, which outputs the parameters of the Gaussian distribution out of which the residual action is drawn. And again, it's additively corrects the base action. So now in more detail, in the first stage, we run behavioral cloning on a set of demonstrated trajectories. So what this corresponds to is just the supervised objective of matching the demonstrator actions in that data set, assuming that the actions are drawn from the distribution, actioning states are drawn from the distribution of that data set. We may also have actions with partly continuous and partly discrete components, in which case we can consider a linear combination of the L2 loss and a cross entropy. And as input, we have the previous frames, such that we can capture velocity and acceleration of objects in the scene and make the environment Markovian. And also some proprioceptive inputs, which depend on the exact manipulator, but could include something like the end effector position, end effector velocity, and the gripper state. And this convolutional neural network is going to output a control action, such as the end effector velocity and the gripper state. As done by prior work, we also apply some data augmentation to make the learning more sample efficient. So if available, we record the demonstrations from multiple viewpoints. And if not available, we can also apply image augmentation, so crops and rotations, the standard things we can take from computer vision. And we can also predict. What we also do is predict not only the next action, but a few actions in the future, as shown in the diagram, such that our policy is able to capture more long-term structure of the task. And this is shown to increase sample efficiency empirically. Now for the residual training, we consider a fixed phase policy. This is to avoid catastrophic forgetting, which can happen when you're learning online and with a sparse reward especially, can be significant. We use an off-policy reinforcement learning algorithm called distributional maximum a posteriori policy optimization. This method is it's an acrocritic method, so it uses a function approximator, so a neural network for the policy as described before, and also for the critic, so for the Q function. For more details, I refer you to the paper. But yeah, so we use a 3-layer neural network for both the critic and the actor. As we are able to reuse the convolutional features, we're able to use rather lightweight networks. And our policy, again, outputs the mean and the diagonal covariance of a Gaussian distribution, out of which the actions are drawn. At evaluation time, this is made deterministic, and the mean is used instead. Again, the resulting action, which is the sum of both policies, is executed in the environment. The residual policy, again, it uses the bottleneck features of the BC network, as well as also gets as input the BC action and the proprioception again. Now for evaluation, we consider 2 task suites of different complexity. So first of all, mine defines 3 simulation tasks: picking a cube, putting a cube in a bowl, and pushing a cube to a target location for a 6 degree of freedom UR5 robot. And with the initial conditions, the initial positions of the objects randomized. We control the arm in task space, so this means we can predict the end effector velocity and the binary gripper state, or continuous velocity for the gripper state. And they are converted into joint space velocities using inverse kinematics. We consider depth frames as input, as well as end effector position and velocity, and gripper state and velocity as the proprioceptive inputs. The second task suite is a droid, which is a higher dimensional manipulator. So it's a fully actuated shadow hand model of 24 degrees of freedom in the hand and 4 additional degrees of freedom in the palm. We consider 4 simulated tasks, so opening a door, picking up a hammer and hammering a nail, in-hand orientation of the pen, and object relocation. So in this task, you have to pick up this blue ball and bring it to a green target. The hand is controlled in joint space, and we consider RGB images, palm and joint positions, joint velocities, and tactile sensors as proprioception. Here are some results for the base policy. So on the y-axis, you have success rate for each policy, given as a function of the number of demonstrations. So depending on the task, we may use as few as 1 or up to about 50 to get a decent base policy performance. And as you further increase the number of demonstrations, the performance approaches the expert performance. We also see that including the proprioceptive signals improves performance for the mind tasks, but not for adroit. This may be due to overfitting, especially towards the end of the episodes when the expert has already resolved the task, and the expert is not is kind of just waiting. So this could be an issue, and it could require some further exploration. In any case, we consider a range of these base policies. We want to inspect how the residual will do, starting from base policies of various strengths. So we have for each task roughly a base policy of 30% success, 50%, 70%, and 90%. And in this plot, we show on the y-axis, in the blue line, how well the residual is able to do starting from the corresponding red initial performance. So the space between the blue and the red would be the improvement that was gained. We see across the board that there is a good improvement. And the training lengths that are given are kind of after the success plateaus. So even significantly fewer frames is enough to already improve over BC. So here are the full training curves. As you see, for instance, for PIC, even using 1 million or 500,000 is already a significant improvement. But of course, until 6 million frames, it will keep improving. Different colors correspond to the different base policies. And the dotted lines are where the performance of the base policy starts. You can see that even from the beginning of training, there isn't a significant drop in the performance, meaning that even though we're doing some exploration, we are able to apply this on a real robot, or it's feasible to apply on real systems where performance should not drastically fall. Moreover, since we are maximizing the reward as defined earlier, what we get as a side effect is that not only are we more successful not only do we manage to increase success rate, but we also decrease execution time. So basically, all the while respecting the environment's velocity limits, we are more efficient at solving the task, resulting after training in a mean reduction of execution time of 21%. Now for some qualitative examples. Here is the hammer task. And first of all, you can see that the residual is on the bottom row, and the corresponding base policy for the same initial condition is on the top row. You can see that the residual is solving the task faster, and it manages to escape some of these failure cases where the base policy didn't manage to precisely center the hammer on the nail, or the base policy may even get completely stuck, as in the fourth example. However, what is difficult for the residual to correct are kind of larger deviations than the base policy, because we're initializing it to take rather small actions, because the base policy is a rather good prior, and we also want to have good kind of safety properties, or not explore like the very large magnitude. One example here on the third column is where the base policy wasn't even close to being in the right angle for the pushing task. And the residual struggles to kind of learn a completely different kind of behavior of recircling back to the back of the cube and trying again. But as we saw from the hammer example, it's better at doing these kind of small adjustments. Another kind of qualitative example is that behavioral cloning is known to suffer from compounding errors. So if your policy makes a small error and kind of starts deviating from the state space that you've seen in the demonstrations, it can kind of get further and further from states that it has seen before, and it kind of generalizes more poorly. And if it, in this case, arrives at the workspace edge, so it kind of like touches the floor or is trying to drive through the floor, there's no way for BC to learn to avoid this state if it wasn't, let's say, present in the demonstrations. So this is kind of a problem when you're using successful demonstrations. You don't learn to, let's say, avoid this action space limits because you're not learning anymore from interaction, only from the fixed data. Whereas the residual can learn to avoid the states through online interaction. In conclusion, we have presented a method called residual RL from demonstrations, which makes few assumptions. So it's very generally applicable to a variety of continuous control tasks, even though we considered manipulation tasks. It's not really specific to manipulation. Also, it only requires demonstrations and a sparse signal for completing the task, meaning that those could be potentially provided by non-experts. It does not require stage estimation, any reward shaping, or base controller engineering, as did the prior methods. We also show in the paper, although I have left it out of this presentation, that it's more sample efficient than RL from scratch, and it's more stable than initializing from BC and fine-tuning with RL. Some further work would include to experiment on a physical robot and propose some ways that we could potentially use the demonstrations as further data during the residual training as well. Thank you. And for more details, please refer to the paper, which is available on arXiv, or you can also view more videos on the project website.
Yeah, thank you very much, Minttu. And now, it's time for the questions from the audience.
Yes, I have a question. So you have a base policy and then you correct with residual.
Yes.
But what is exactly the policy? Are these the coefficients in the neural network, or what is the policy?
Yes, in this case, both the policies are parameterized by neural networks. The base policy is a convolutional neural network, and the residual is a kind of three-layer fully connected neural network.
So these are two different ones. There's a basic one, and then there's a residual one. But
let me go back to the figure. So f of f theta here is the CNN.
Yes.
And this is trained in the first stage because we have kind of denser supervision in the BC stage, because we have, for each stage, we have the correct action, let's say, for the demonstrator action. And in the second stage, we have a very sparse supervision signal from the reward. So we train only a small policy network in addition.
It's behind. In some way, it takes the output of the basic one and then it makes something. Okay. So I understand. Okay. Okay. Mm-hmm. Okay. Thank you.
So, are there another questions?
I have a question about neural network to extract feature from the image. Have you used a pre-trained model to extract feature from the image, or you train during the RL task training?
In this case, we train using the demonstrations. So the demonstration data set is where it's trained entirely from scratch. But yeah, it could be interesting to consider some pre-trained data set as well. It's just a bit not clear how I would generalize from. I mean, the data sets would have to be, I guess, kind of relevant to robots.
Oh, okay. I see. Thank you.
So, are there any questions? more? Okay, if not, I can ask the two. So yeah, my first one is that am I right that you didn't use any regularizers in your objective functions or like dropout layers in the network?
We use some layer norm in the network, but yes, in terms of objective, I believe there is a regularization in the NPO algorithm. So
okay,
this is the algorithm that is used for the residual itself. But no, there is no regularization in terms of staying close to the demonstrations, which could also be an avenue for further work.
Mm-hmm. Okay, I see. Thank you. And the last one from my side. So you used for as an input, for example, you used the history of 3 previous frames. And actually for the predictions, you used 4 values, like the current action and some future actions for 10, 20, and 30 time steps. Yes. So my question is that are there both like the 3 frames and these 3 future time steps play a role of hyperparameters in the system, or you have some intuition behind why you choose exactly this size of history and the future, the size of future actions?
Yeah, that's a good question. So I would say that, I mean, potentially both could be considered hyperparameters, but for the length of the history, using 3 allows you to consider both the velocity, or infer something about both the velocity and the acceleration of anything in your scene. Mm-hmm. Whereas if you had only 2, you wouldn't be able to tell only about velocity, etc. For the action targets, I think this is a hyperparameter. I mean, it was used in a prior work, but yeah, could also work with other values.
Okay, yeah. Thank you very much.
Thank you.
So yeah, if there are no more questions, I think we can move to presenter number 2. So thank you, Minttu, for your talk. Yeah, and the next speaker is Ilia Igashov. He will present the work about graph neural nets for protein model quality assessment. And Ilia is from LJK and MIPT laboratories. So yeah, Ilia, if you're ready, I can give you the floor.
Yeah, thanks, Artem. Hello, everyone. Do you hear me well?
Yes.
Okay, great. Yeah. So my name is Ilia. I'm from Moscow, but currently I'm located in Grenoble. This year I'm finishing my master studies at MIPT and UGA. And today I'll talk about applying of graph neural networks in protein model quality assessment problem. So we're going to look on this problem, and then I'll explain 2 methods that we developed in the last 2 years. We did this work in collaboration with the Life Science Center of Vilnius University, and also some students from MIPT and UGA took part in it as well. So to start with, let's talk a bit about the protein structure prediction problem. This is a well-known task that has been of interest to a lot of biologists during the last 50 years, and that experienced a lot of boost in attention from data scientists and mathematicians in the recent time, that eventually resulted in unprecedented achievements of AlphaFold from DeepMind last year. So the task is having a sequence of amino acids of a protein as an input. The aim is to predict the 3D structure of this protein. Having then the native structure of this protein as ground truth, for example, the structure can be experimentally observed. We can evaluate the quality of the predicted 3D model using different metrics. There are several common metrics that are used for comparing 3D models and native structures. And without going into details, the idea of this metrics is just to compare residues and coordinates of these residues between 3D model and native structure, and to output some score that means the similarity of the 3D model. And there are several scores, and they can be divided into two groups: local scores that assess each residue in protein independently, and we have just the score of each amino acid, and global scores that just output one value for the whole model. However, in the real world, we usually don't have target structures available because experiments are pretty expensive and take a long time. So yeah, here appears another task to predict the quality of generated 3D model without having a native structure available. So that's what we call protein model quality assessment problem, and that's exactly what we've been working on. So basically, the task is to predict one of these metrics. So why do we want to solve this problem instead of concentrating on protein structure prediction itself? Well, first of all, obviously, because models are still not perfect, and we want to know their quality without having ground truth data. Common example of application of MQA method is to choose the best model among many similar ones that are generated. Also, MQA methods can be used as components of more complex protein structure prediction systems. And other applications include localization of problems in the generated model, for example, to choose the most problematic residues. Also, MQA methods can be helpful in refinement tasks, and even in finding protein-protein interactions, prediction of these binding sites, also MQA methods can be used. So talking about existing methods, I would classify them into three main groups. The first group contains various unsupervised methods that were evolving since the earliest times. So these methods usually include different potential-based algorithms, molecular dynamic simulations, statistics, and so on. The next group consists of supervised models that operate on some pre-computed descriptors. The common example is an SVM model trained on different potentials. And the third, most recent group is end-to-end methods that are mainly deep neural networks. And among others here, I would highlight geometric learning methods that operate on geometry of 3D molecules. And the most successful one is 3D CNNs, when we just apply 3D convolutions on voxelized space around this model. Yeah, and the agent that stirs up interest in this community to predict structures and to predict the quality of the predicted structures are several blind challenges, such as CASP and Cameo, for example. So basically all state-of-the-art methods participate in at least one of these challenges, and it's kind of chief justice to assess if the method makes sense or not, because it's blind. So we'll talk a bit about it later as well. So when we started working on our MQA method, we set up several requirements. First of all, since a lot of functional characteristics of molecules are dictated by its shape, we believe that geometry is crucial for understanding physical and chemical properties of molecules, including protein functions. So we wanted to use geometry at full breadth in our solution. And we wanted to minimize the contribution of different chemophysical information and to keep only basic properties, for example, chemical bonds between atoms. We also wanted to reduce the number of trainable parameters compared to existing geometric learning MQA methods. For example, in 3D CNN, number of trainable parameters was about 2 million. And yeah, the idea was to learn representations right in our pipeline without using any handcrafted features. And by minimizing all additional prior information that can be passed to the algorithm along with the input model. So taking into account that we work on proteins, the solution was pretty transparent. Graph neural networks and representation of proteins as graphs makes much sense. The only question was how we can include geometric information into this graph abstraction. So protein fold into specific three-dimensional structures, and the main contribution of this fold is basically because of interactions between atoms, and these interactions rapidly decay with the distance. So we decided that using some tessellation of the 3D space would be very useful and would allow us to get this implicitly include the information about interactions between atoms into our graphs. So Voronoi tessellation on 2D is illustrated in this animation, basically having a set of points in a space that can be called centroids. We want to build a partition of the space that has the following property. Any point in the space belongs to the region that corresponds to the centroid that is the closest one to this point. So in our case, centroids are atoms, and we work in 3D space. For building tessellation, we used the efficient and robust algorithm designed specifically for tessellating 3D molecules. And this algorithm is called Voronota. In fact, this approach, including building the graph based on tessellation, was pretty new for proteins, as before normally protein graphs were built based on distance maps between atoms. All right, so staking all discussed steps in one pipeline, we get VORCNN, which is graph convolutional neural network that operates on tessellation graphs of molecules. And the workflow of this pipeline is following. First of all, we compute Voronoi 3D tessellation of the protein model. Then we build a weighted graph based on this tessellation. In our graph, nodes correspond to Voronoi cells of atoms, and features are just one hot representation of atom types. And we also have several types of edges. Basically, the first type is contacts between these Voronoi voxels, and weight corresponds to the area between area of the contact. The second type is covalent bonds, and also we additionally split each of these two types into several subtypes based on additional information. So for covalent edges, we split them into 3 subtypes based on the type of covalent bond, single, double, or aromatic. And for contact edges, we split them into 6 subtypes based on the sequence separation factor, which is the distance in a graph between residues that correspond to the nodes of this graph. So for example, if we have 2 atoms in one residue, in the same residue, sequence separation will be 0. If they are in the neighboring residues, it will be 1, and so on. And finally, we just pass this graph into graph neural network that predicts local scores of protein model. So this is the architecture of our network. It consists of 3 main parts. The first block, which is called encoder, just transforms initial node features, which are one-hot encoded atom types, into a more compact representation. It consists of linear layers and activation functions. The second block is the main block of our network. It's called body, and it learns geometric representations using graph convolutional operations. In our case, convolution is essentially a standard message passing mechanism where for each node, we simply aggregate information from its neighbors. Basically, for each node, we take feature vectors of its neighbors, multiply them by some trainable metrics, sum up, and also add nonlinear compute activation on top of this result. So the formula that is presented here is pretty basic. In reality, we have several types of edges, and for each type we have separate trainable parameters, but the main idea can be represented in this formula. And this block also contains graph pooling operation designed specifically for proteins. So prior knowledge about protein structure allowed us to design an efficient downsampling of the graph based on the fact that all atoms are naturally grouped into amino acids or residues. So after pooling, we operate on the residue level graph. Basically, we just aggregate all the features within each residue. And the last part of the network is regressor, a simple linear lawyer with nonlinearity that predicts local cut scores. The total number of parameters is around 20,000, which is much less than number of parameters in existing geometric learning MQA methods. We evaluated WAR-CNN on the data from two cusps, two challenges, and for obtaining global scores, because normally community is interested in global score, but especially when we assess the ability of our MQA methods to output the scores. Since we predict local scores, we just aggregated them to get the global one. And the table shows we outperformed the state-of-the-art methods in several metrics, and even for several metrics that compute the similarity, although we trained on the cut score. And for local scoring, we also outperformed state-of-the-art. And we also built a distribution of scores that WAR-CNN predicts for models and targets. And you can see that it can distinguish well between these two types of structures. And there are several examples of WAR-CNN predictions. So on the left part, there are two proteins, and for each of them, we illustrated WAR-CNN prediction on the target structure. We see that they are uniformly good and uniformly high. Then we illustrated WAR-CNN prediction on some model that is not perfect. And on the third column, there are real cut scores on the same model. And on the right, we can see how WAR-CNN detects binding sites of the proteins. So we took just two obligatory complexes that consist of two parts. And we firstly assessed the whole complex at once, and we see that this score is also uniformly high on the whole model. And then we assessed each part independently, and it's clearly seen that binding sites are underscored. All right, so WAR-CNN performed pretty well, but we decided to move a bit further. What if we replace the standard message passing mechanism that was used in WAR-CNN for making convolution, and that basically consists of linear transformations and aggregations? So what if we will try to replace it with something more generic that also takes into account special relationships between nodes? So there is an example of images. So the issue that arises here are pretty common for graph learning problems. So opposed to images, we have irregular domain, and different graphs have different topology. In addition to, we want to preserve permutation variance that is, for example, achieved in message passing because of aggregation. And also we want to be rotation equivariant because if we will work on some 3D information, so we don't want to be connected with some particular basis that we choose. So we thought a bit and came up with the idea that functions on spheres can be useful in this method. And basically, we can represent our data as a hybrid between graphs and point clouds. Basically, we work in Euclidean 3D space, and we don't care about particular topology. In addition to, we keep staying permutation invariant by design. We keep aggregating node information, but just in a different way, not like it was done in a message passing mechanism. And the only question is if we are able to achieve the rotation equivariance property. And it turned out that yes, we can achieve it, and we can actually achieve even rotation invariance of the whole model because of our data. Basically, all proteins have a peptide chain that connects residues between each other, and this peptide chain can be our invariant. If we do all operations with respect to this chain, we won't depend on any changes of external basis, because we consider our protein molecule kind of rigid body, and we are connected with local coordinate systems. So that's what we actually did. For each node in our graph, we build a local coordinate system that is strictly connected with vectors between C, C alpha, and N atoms that exist in each amino acid. And then we set up a unit sphere with a center in our node and projected all neighbors onto this unit sphere. So having a local coordinate system that is associated with the central node, we obtain local coordinates of these neighbors and write them to the matrix that is written in the bottom of the slide. So it's kind of adjacency matrix, but it contains mutual local coordinates of nodes. It's non-symmetric, and it's basically, it contains just local coordinate of nodes. So turning back to our filters, we define convolution on the node as a sum of products of some function f defined on the sphere with the feature vector of each neighbor of the node v. The value of function depends on the position of a neighbor. So we can say that we kind of scan the neighborhood of the node with the sum filter f. F can be any functional sphere, and we represent it as a approximated spherical harmonics expansion. Coefficients are trainable, and basically we are not restricted by a certain form of a filter. And the convolution lawyer can be written in the such form as it's shown here. So here we consider that this is a notation YLM is a matrix of values of spherical harmonics that are computed on local coordinates that are stored in initial adjacency matrix. Also we should emphasize that if we set the maximal order of expansion to 0, we just get the standard message passing formula. So we trained and tested SGCN with maximal order 5 and 10, and there are results of the global scoring of these models on CASP 13. So we can say that the main achievement here was that we are on par with the state-of-the-art methods, despite two facts. First, we operate on the residue level data, oppositely to WRCNN that starts with atom graph. Here we have residues. And we fully rely on geometry in this methods. We don't have any chemical information except the type of residue in the very beginning. And there are some examples of learned filters which correspond to the values of the order. And also an example of how SGCN assess the complex. So basically it's the same complex that was used for WRCNN, and we see that here binding interface has lower scores as well. And finally, in the last summer, we participated in a blind challenge CASP 14. And in this challenge, we tried different modifications of our both models. For example, one of WRCNN modifications also uses some convolution information as input. In general, both WRCNN and SGCN were ranked very high in several assessments. So we're pretty happy with it. Okay, thanks a lot for listening. I think that's all.
Thank you very much, Ilia. So yes, are there any questions from the audience? Okay, maybe I can ask something. Am I read that in your task, the architecture of the network for both like Boro CNN and the spherical convolutional network plays a really important role. So yeah, it's really important which architecture to choose for the task. So yeah, my question is, did you try to use kind of neural architecture search to search the optimal architecture, yeah, to increase the performance?
Yeah.
Or you did this manually?
Yeah, thanks for question. Yeah, normally we just did it manually, returning back to CNN architecture, for example. So here, as I said, we have 3 blocks, and basically we just experimented with each of them. We pretty early agreed on this general structure that we should have some encoder that will operate on initial features and get some more compact representation. Also, we wanted to have some part that learns these representations using convolution operations, and then yeah, just for regression task. And we just tried different options. Yeah, so basically it was the most optimal one, but we did it manually.
Okay, I see. Yep.
Yeah.
Yep.
How does your spherical harmonic basis functions relate to electron orbitals, which are also spherical harmonics?
Yeah, so basically, I think that it's not connected in this in our case, because we here we use spherical harmonics as a basis for like functions on spheres, and the idea is to try to represent the function on the sphere using this expansion by spherical harmonics, of course, with some approximation by cutting choosing the maximal expansion order. And yeah, so idea is it's totally geometric. We just want to have some functions on these spheres, and yeah, we use spherical harmonics.
Yeah, but I guess the point is that the local geometry of the protein chain, the backbone, is determined by local spherical harmonics. And what you're trying to do is to relate that, its electronegativity and van der Waals likelihoods for pairing and everything else, to slightly larger scale structure using spherical harmonics also. But it seems that, there should be some kind of mapping between local electron orbitals, not necessarily on single nodes, but maybe, shared bonds between adjacent nodes and things like that. There should be some relation between that at a fine scale and your spherical harmonics at a coarser scale.
Yeah, it makes sense. I think it's a really interesting idea. But actually, yeah, we didn't. So basically, we didn't think about it. So, but it would be nice to check and to work on it.
Yeah. Well, one suggestion that follows from that is that maybe some kind of cylindrical harmonics based on links as well as spherical harmonics based on spheres could be useful.
Yeah.
Okay. Thanks.
Cool. Thank you.
So are there more questions? Okay, yeah, I have the last one. For the task of quality assessment, and I read that you used the so-called CAD score for the ground truth to compare with. Yeah, so my question is more abstract maybe. So are there any other ways to qualify the assessment in this task? Because it appears that CAD scores, as for me, are also the way to measure the performance of the model, to measure the quality of the model. And if the CAD score itself is not so nice, but you treat it as a ground truth, So yeah, it will be kind of problem. So do you have some another way, or it's only one for now?
Yeah, you're totally right. These scores are non-perfect, of course. But basically, there are several that are the most common for this community, and CID score is one of them. So on the slide, there are two others that are also pretty popular. And actually, there is no one like opinion of which one is the best, but it also depends on what you want to learn, I guess, because in our case, we initially, as I told, we are trained on local scores, and for local scoring, we have only 2 scores out of these 3 because GDT doesn't have local scores. So there are several ones, and we just choose one of them to train on.
Okay, I got it. Yeah, thank you. So if there are no more questions, I think we can finish our session. Yep. So thank you, Ilia, one more time. And I guess now we'll have a little break for half an hour and continue the next session. So thank you very much, all of you, and see you.
let's begin.
Yes. So, hello everyone. My name is Fassam. Yesterday I did a presentation, and so this afternoon I will be the junior chair for the rest of the session. And we will start with the presentation of Artem, who is a PhD student at UGA and Criteo AI Lab. And he will be giving a talk at, on Uplift modeling with the generalization guarantees. So is everything okay, Artem?
Yes, Hussam, thank you.
Yeah, great.
So I will share my screen. Can you see my screen?
Yes.
Okay. So hello everyone, my name is Artem Betlei. Today I'm here to present our work about Uplift modeling with generalization guarantees, which was done in a Criteo AI Lab and Laboratoire Informatique Grenoble with my supervisors, the stage gamer and Masiriza Amin. So our main task is to predict individual uplift or conditional average treatment effect using the data from randomized controlled trial. So if you look at the formula, you can see that uplift U of X for the user X is simply the difference between probability of success being in treatment group G equals to T and control group G equals to C. So the problem here is referred to the causal inference domain, and it's called the fundamental problem of causal inference. So the problem is that we cannot observe one user into in the two groups, treatment and control, simultaneously. So we only can assign user to treatment group or to control group and never to the both. So that is why U of X, the true uplift for the user X, is not observable. And the raised question is how to evaluate performance of uplift models then. So the idea used in the community is to compute the group-based uplift instead of individual one for the model evaluation. Because for the group of users from treatment and control populations, we can compute the uplift and consider it as a true one. So the idea is to rank the population, rank all the users by their predicted uplift score produced by the model F, for example, uplift model. For this ranking induced by the model, we can compute uplift cumulatively. So if you look at the picture, for example, you can see the three different curves. So these curves correspond to different uplift models. And if you look for the blue curve, for example, you can see the blue point VF 0.5. So it means the cumulative uplift of the model F for the first 50% of the population induced by ranking produced by model F. Yes, and if we when we compute when we draw entire curve, when we compute this cumulative uplift for all the proportions of the users induced by ranking, we can summarize this information by computing the area under this curve. So the main metric in the field, which we consider here as well, it's area under uplift curve. We can compare, for example, two different uplift models by their areas under uplift curves. Yes, so having this model evaluation procedure, we can pick the best model, for example, and use this model to target treatment on the next cohort of individuals. So yeah, we can say that maybe we only need to target treatment to some first ratio of the users, let's say first 30% of the users due to the budget constraints, for example. And for this, we use the ranking of the best model, and we successfully target treatment for the first ratio of the individuals. Yes, so for our contributions, we present the first generalization bound for area on the uplift curve. Then, as we already know that the metric really depends on how we rank the population by their uplift scores. With this knowledge, we produce the ranking-based algorithm that directly maximizes a lower bound, which we presented for AUC. And we can use this algorithm with different families of models like linear or deep models. And finally, we show the big empirical evaluation when we compare different variants of the bounds and cover the tightness of these variants. Then we measure the effectiveness of the bound for hyperparameter tuning. And we present the performance of our algorithm on two real-world data sets compared to existed baselines from the literature. Okay. So the first and I think the main building block of creation of the bound is our proposition 1 here. And this is a decomposition of AUC into the weighted sum of two bipartite ranking risks for group treatment and for group control. So I remind you that ranking risk R hat is simply the number of incorrectly ranked items produced by the model. The main idea is to work separately with this bipartite ranking risks to formulate the generalization bounds for both of them, and then apply union bounds to obtain the bound for AUC. So what is the difficulty of the bipartite ranking task itself? Is that now in this task, we instead of using the elements themselves, like samples from positives and negatives, samples from positive and negative classes, now we use the pairs of the elements. When one element of the pair is positive, the second one is negative, and we solve the classification problem on the top of this pairs data. And if we look at the example here, we can see that, so x1 plus, x2 plus are positives, x1, x2, x3 minus are negatives. And if we form the pairs from these elements, we can see that the two pairs that I highlighted contain the common elements x1 plus. And it means that the data for bipartite ranking is not independent anymore. And this kind of data is called interdependent data. And we need to solve somehow this problem of interdependency, maybe to decompose somehow this interdependent data into the sets of independent data to work with independent, because only with this assumption we can formulate some generalization properties, for example. And we do exactly this. So at the dependency graph on the right part of the image, you can see that we create so-called proper fractional cover, exact proper fractional cover for this type of data. And so this cover consists of number of sets. So I will highlight these sets. So blue one, yellow one, and the red one. And you can notice that in each of these sets, so the pairs in one set doesn't contain the same elements. So in other words, within the set, the data is independent. Yes, and now when we decompose the entire data into the series of the sets, for each of the sets, we can formulate for each of the sets the capacity measure, for example, and then we with this technique we present the capacity measure for the full data. And we use for this the Rademacher complexity, which captures the ability of function class to learn random noise. And you can see that we formulate we can formulate the Rademacher complexity within the set. So we have particular Rademacher complexities for each of the sets, and so-called local fractional Rademacher complexity, which is the important definition in our bound. It's simply the weighted sum of Rademacher complexities in the sets. So yeah, local fractional Rademacher complexity summarizes the complexity of the full data, or the full cover. So now when we presented the main building blocks, we can present theorem 1, which is the generalization bound for AUC. And the bound, it's a lower bound, and it consists of the 3 main terms, namely empirical term, which is exactly from the proposition 1, and also 2 additional terms, the complexity term, which is based on local fractional Rademacher complexities for treatment and control groups, and the last, the data term or residual term, within which we have only the constants, data-dependent constants. Now the good question is, okay, if we want to use this bound in practice, for example, for hyperparameter tuning, is it enough to optimize only the empirical term, or we can somehow try to add a complexity term into optimization problem? Because optimizing the sum of the 2 will bring us the guarantees exactly in the algorithm. So yeah, the question is how to estimate the local fractional Rademacher complexities inside the complexity term. For this, we use our proposition 2, which is the bound for local fractional Rademacher complexity for the group. You can notice here that we use the specific class of the functions, which is the class of linear functions with bounded variance and bounded norm over the weights. That, as I already said, we can apply the algorithm for deep nets as well, for deep models. And yeah, for this, we just formulate the proposition 2 over the representations of x, phi of x, instead of x itself. So we can use some deep network, and as the last layer, it will be the linear layer, for which this bound for Rademacher complexity will hold. Yes, and as we already bound local fractional Rademacher complexity, we can compute this bound and use it for the optimization itself. And it's exactly what we are doing in our optimization problem. So we call this objective function AUC max. And here we minimize the sum of the empirical and complexity terms. So just pay attention that instead of the indicator function inside of bipartite ranking risks, which is non-differentiable, we use instead the differentiable surrogates as this this surrogate can be polynomial or logistic ones. Yeah, and it's kind of hyperparameters, so you can try different surrogates and say what is better by experiments. Also, we have here the complexity terms, and yeah, we can add it to optimization. And because of the presence of complexity term, we have additional constraint in the optimization, which is the constraint on the norm of the weights. Yes, and as a result, the big lambda plays a role of the hyperparameter in our algorithm, like additional one. Yes, so now we are ready to present the benchmark and experiments. For the benchmark, we used two real-world data sets from the field. So the first one is Hillstrom email marketing data. Yes, and the second is Criteo Uplift version 2, which is our data set. And the Hillstrom one is based on the email marketing campaign of some internet-based retailer. Criteo data consists of several incrementality A/B tests. And yeah, you can notice that there is a big gap in the data size between the two. Dimensionality are similar. Dimensionality is similar. And also we can notice that the treatment ratio here it's almost 0.5, and in Criteo data the treatment group is bigger than control one, which is the additional difficulty of the data set. Also we can pay attention here that the average uplift is lower in Criteo data than in Hillstrom one. So the uplift signal is lower in the Criteo data. Yes, now we can move to the results. We were interested in the several things for the experiments. So the first one is that did we choose the right technique to formulate the generalization bound? Because now if we compare, if we decompose, AUC into the weighted sum of bipartite ranking risks, we can formulate generalization bound for bipartite ranking risk, in different ways. And here we compare our technique based on local fractional order macro complexity to the two ones from the literature from these papers. And both of them are based on some concentration inequalities. And we measure for this the gap between the expectation of AUC and the bound value. So in other words, we measure the tightness of the bounds. And we can see that our technique based on the local fractional order macro complexities from this paper is outperform two another techniques, and that's the evidence that we chose the right technique for the bound. The experiment was done here on the Hillstrom dataset, and also for the Hillstrom we measured the performance of the algorithms of the performance of the baselines and of our AUC max algorithm. On the test dataset, test split, after some several random train test splits. Yes, and here we compare test AUC with at the same time comparing the number of parameters of the model and the computation time. So the standard of the computation time here, like the default value, is the time of baseline two models method for uplift modeling. And yeah, the conclusions that we can create from this table is that all of the methods are working approximately the same in terms of the statistical significance. But yeah, it's the general problem in the task. So it's really hard to obtain something statistically more statistically significant better than the others. That also even the minor differences could be really important if we use this uplift models in the industrial cases, for example. And we can see here the top two results in the bold font. And AUC max, the deep version, is the top one. At the same time, the algorithm, even as it's a deep one, is maintain the relatively good computation time. actually, in the appendix of our work, we compared the basic version of AUC Max, which is just empirical term optimization, based on some model evaluation techniques like cross-validation, for example, five-fold cross-validation, with a full AUC Max objective with complexity term. And the idea was that optimizing complexity term itself, which guarantees the generalization, can reduce the computation time and can give the more efficiency for the algorithm. And yeah, you can see particular results in the appendix of the paper. Yes, then our second experiment was about to check the hypothesis that in general, point-wise algorithms, namely the algorithms based on the bipartite ranking, perform better than point-wise baselines. And yeah, for this, we draw the uplift curves for 5 algorithms, and we compare the cumulative uplifts from the beginning of the ranking until the first 30% of the population. So in this picture, we can see that all the pairwise methods, so 2 hour methods, red and purple, and SVM for differential prediction, which is green one, outperform the point-wise baselines, which is the evidence of correctness of our hypothesis. Yes, and finally, we present here the experiment on the Criteo Uplift version 2 data. The values of test AUCs for the baselines are also almost the same for every models. And here we also report the top 2 in the bold font, and we can see that both AUC Max deep version and SVM for differential prediction, which is also pairwise, outperform all the baselines. Yes. Yes. So just to conclude, we presented the data-dependent generalization lower bound for the main uplift modeling metric, area under uplift curve. Then we formulated the learning objective that optimizes a derivable surrogate of this metric, of the bound of this metric. And at the same time, algorithm is usable with different models like linear or deep ones. By experiments, we showed the effectiveness of the AUC Max algorithm and yeah, competitiveness against the relevant baselines from the literature. And as a future work, we were interested on several things. Namely, we are wondering to compare our proposition 2, which we created, with the novel techniques of bounding local fractional Rademacher complexities for deep models. And also, it could be interesting for us to try to adapt our bound, which we produced here, to other uplift models like shared data representation, for example, SDR, or Tarnet, treatment agnostic representation network. Yes, so that's the end of the presentation for me. Yeah, thank you very much.
Thank you so much, Artem. It was a very interesting presentation. I think we learned a lot. So are there any questions from the audience? Because otherwise I have a lot of them. So
sorry, it's my mistake to stop the sharing of the screen.
No
so yes. Okay, this one. Yeah.
All right. So my first question is about the ranking strategy. The ranking risk measure that you use is bipartite, right? So I guess it's because you have in that case treatment or not treated. Would you, if I'm not mistaken, correct me, please, if I'm mistaken. If would you
go ahead?
Yeah, if you had something like several treatments, or let's say, for example, continuous treatment, would it be like a completely different metric, or would it be easy to adapt that metric?
Yes, that's a good question. And right now we can extend our method for continuous outcomes, because here, as you may notice, we used binary outcomes. So
yes.
yeah, and
also sorry, so it's about the outcome. It's not about whether you treat it or not.
Okay, yes. So
okay,
yes,
about...
as for the outcomes, indeed, we can extend our method for continuous outcomes, because we just slightly reformulate. So if maybe I can show you here at this slide. So you see the sum, these two terms here. Now the interpretation is the count of the successes of the positive outcomes in the part of group T, part of group C, in the first ratio of the users. But yeah, instead of this, we can compute here. It will be actually the same formulation, sum of y, but instead of 0 and 1s, we will have continuous values. Yeah. And we can still decompose the AUC into the sum, maybe not bipartite ranking risk, but I would say that we will turn, in this case, in the case of continuous outcome, into some kind of listwise ranking. So yeah, instead of bipartite ranking, it will be listwise one.
Okay.
But yeah, we did actually some work already. Yeah, in terms of this extension to continuous outcome. Yeah.
Nice. Okay. So in terms of of the AUUC objective, I don't know. I did not write down the number on the how do you say the slide? Yes, thank you. This one, great.
The slide page, okay.
Yes, slide page. Yes, indeed. So I see that you add the Rademacher complexity here in your objective function, and then you have you say this additional constraint. So first of all, my question is, why would you add like the Rademacher complexity without any sort of penalty term where you have, for example, a lambda or any constant that you would put in front of it, so as to maybe rescale it? I mean, I'm asking like this very naively because from a machine learning perspective, when we add this sort of complexity, regularization or whatever, we are somehow used to have a constant in front of it. And the second sub question is, could you repeat again, sorry, why you have this additional constraint and which optimizer do you use to tackle this linear constraint that you have on W?
Yes, okay. So first of all, you see in our proposition 2,
yes,
we tried exactly to solve the question how to include local fractional Rademacher complexity into the optimization problem. And as we know that Rademacher complexity is a capacity measure, and it's defined for the class of linear functions. Yes.
Okay.
We need to bound it somehow to be able to compute not the directly Rademacher complexity, but at least the bound on it.
Yes.
And you see here we have the bound, and we have the some terms which we define. So yeah, now we will work only with this part in the optimization problem. And here we can see that, for example, mg plus, it's number of positives in group G. It's a data-dependent term. Delta, it's also the parameter which we like for create the probability with which the bound will hold. And here two terms are square and square. It's exactly the bounds on the value of the feature. here and the bound on norm of the weights respectively. So now, we need to, for example, if we define the big R, big lambda, we can estimate this bound for the macro. And we said that, we will fix this big R, but we will use, we will try to minimize big lambda in order to minimize this overall bound for the macro. And it's exactly why the constraint of weights appears here.
Okay.
You see, and really a small remark is that here we have the bound for the variance of the function f, small r, and we need to estimate it somehow as well, because in the full formulation in the paper you will meet this small r, in the theorem 1, for example, and for this, we use here, actually it's already this lambda big lambda square, large R square. It's exactly the estimation of small r of this bound on the variance. So you see, we go with a series of expressions into the from original local fractional or the macro complexity definition into the optimization of big lambda also only.
Okay.
So yes, and that's why, and you asked how to optimize this big lambda. We just create the grid of big lambdas. So we discretize this parameter into the grid of values, and we use this as a hyperparameter. So we just try different lambdas.
Okay. Okay, then thank you for your response. I think we are about time to go to the next presenter. If anyone has any other questions or. Okay, well then, thank you so much, Artem. Honestly, it was a very good presentation. I mean, personally, I liked it and I learned a lot of stuff. So I hope the others enjoyed it as well. So our next speaker is Carlos Brito Pacheco from LJK-UGA. I will let you introduce yourself, Carlos, and also have a talk from you on shape optimization of thermal devices and introduction to density and shape optimization. Thank you so much.
Thank you. Let me just share my screen. Can you hear me?
Yes, I can hear you well.
Okay. So hello, everyone. My name is Carlos, as has already been said, and I'm going to be talking to you about the automated optimization of thermal devices. So this will be a light talk. It'll be just an introduction to density and shape optimization, and it's a little bit different to the talks we had throughout these 2 days. But I hope that at least I can interest you or maybe give you some ideas that you can apply in your research. Okay, so the talk is divided into 3 parts: the introduction, the optimal distribution of conductive material, and optimal two-phase designs. We will see what this means in due time. So for the first part, what is shape optimization? So shape optimization is basically the development of mathematical techniques aimed at predicting the optimal shape of a structure. So basically, given some criteria, we seek to minimize it, as in maybe supervised learning, and find the best structure. So here the variable is the structure. And it will allow us the automated calculation of these designs, satisfying the chosen constraints. So that means that we will be able to design an algorithm and implement it in the computer. So in fact, this area has a lot of influence on other areas of science, so architecture. So this paper details how to optimize the floor of a building, geology. This paper that I cited here looks for the best or for the optimal design in preventing landslides, and material sciences and fluid mechanics. In particular, this paper talks about the optimization of weakly coupled thermal fluid devices, and many, many more. These are just to give some examples. So for some numerical examples that you might get or you might expect when applying these techniques are shown here. So in the first two, it's more or less the optimal design of a heat dissipation device, which is our topic of this talk. And in the lower part, you can see the optimization of landing gear of some aircraft and the optimal or the automated yielded design of a bridge, totally automated from an algorithm. So with that being said, let us begin. So for our introduction, we choose to solve this following problem. We wish to minimize the mean temperature of a device utilizing the least amount of conductive material. So we assume that this device is spread on some domain D and subject to a heat source F. So this heat source might be uniform on the whole domain or might just occupy this area. And it will have an absorbing boundary condition, so a Dirichlet a homogeneous Dirichlet condition, and in an insulating wall, so a homogeneous Newman boundary condition. So maybe a physical example of this is a microchip. So we have liquid cooling that carries the heat away, and this is the domain D. So, and the heat source is uniformly spread on the microchip. So what is how do we formulate a problem like this mathematically? So first we have to ask ourselves, how do we model the state of a system like this? Well, we use partial differential equations, of course, and we say that the temperature U gamma according to the conductivity distribution gamma is given by, well, the heat equation, the classical heat equation with anisotropic, in an isotropic conductivity media. And we have the Dirichlet condition that we talked about here, and the homogeneous Newman boundary condition on gamma n, which we talked about here. And we aim to optimize the distribution of the conductivity gamma on the domain D with respect to some criterion J gamma that I will define now. So before doing this, we need to fix a little bit. We need to say which kind of conductivities or which kind of designs we look for. So of course, conductivities cannot blow up in the physical world and cannot be exactly zero. So first of all, we bound the conductivities. We say that they're in L infinity, and we want to control it by these bounds beta and gamma. And we seek to solve the following problem. We want to find the infimum of this given criterion J. So this is the mean temperature. So this is the temperature that characterized by this equation. And we want to also minimize the amount of conductive material. So this is gamma. And L is just some Lagrange parameter, which of course has the usual meaning that as you increase it, it penalizes the amount of conductive material used, while if it is very small, it does not penalize it as much. So what are the mathematical ingredients to solve a problem like this? Well, usually when you minimize a functional or function, you want to apply some kind of gradient descent, gradient algorithm. And for this, you usually calculate the Frechet differential. You find the descent direction, K, and you apply some kind of descent step. So how do we compute the Frechet differential of this J gamma? Well, the Frechet differential of this is obvious. So the real problem is here because of this guy, because this is the solution to a PDE. So we need to compute the map, the differential of the map of this guy. So the following theorem actually gives us the solution, and it says, it reads, the differential dj is given by this, is equal to this. So this is, as you can see, directly the Frechet differential in the direction k, and the Frechet differential of this is characterized by this weak formulation. So the important thing to note here is that the Frechet differential is characterized by the weak formulation. So we need to solve this weak formulation, but we are able to characterize it. And how do you prove a theorem like this? So the only real problem is proving that the map gamma goes to U gamma is differentiable and characterizing the Frechet differential by the weak formulation. So I have written a sketch of proof here. And well, we let a direction so small that the perturbation is also in L infinity. We consider the solution U bar to the perturbed problem at conductivity gamma plus k, so in the perturbed case. And this is the weak formulation. And the main ingredient comes here. We recharacterize U bar as the solution to a root finding problem, where F is defined by this. So just move this guy over to this side and it'll give you F. And now we can apply the implicit function theorem at this point, so 0 in the direction 0. No, sorry, and at the point use and point 0 U gamma to prove that the map K goes to U bar K is a differentiable mapping. And then we simply compute the partial differential with respect to K. So, okay, having proved this, now we note the following problem. The expression of the differential is not suitable from a practical point of view. It depends on the solution to this guy, which depends on the direction K. So this is not, you cannot exploit this in practice because, well, you would have to somehow solve this for every K, and it's not feasible, not tractable. So the solution is to simply introduce an adjoint state P gamma. So theorem, the differential will rewrite for every K in L infinity, for every direction, like this. So now we have explicited the differential in terms of K. And the new addition is this P gamma, which is characterized by this weak formulation, which again, the actual precise expression of the weak formulation is not that important. What is important is that we are able to explicit the differential in terms of K. And this leads us to identifying the L2 gradient of J gamma. So we can actually just choose minus J prime gamma as a descent direction. Just substitute the negative of this guy here, and you will see that it's obvious that it's a descent direction. So applying this and a naive descent gradient descent algorithm, we are able to get these first results. So there are two problems with this. We have continuous changing conductivities. So this is not physical. There's no material on Earth which has continuous changing conductivities. You cannot just go from, it's not physical. You either have a conductivity at one segment of your design, or you have another conductivity. And the other problem is that the choice of descent direction is not appropriate. So if you notice here, we have some oscillations going on, and this is due, or in partly due to our choice of descent direction. So so how do we fix these two problems? So problem number one, instead of continuous densities, we would like two-phase designs. The solution to this is well known. It's just we can apply some numerical treatment and use the SIMP approach, so the solid isotropic material penalization approach. So how does this work? We now consider that gamma indicates the density of conductivity at some point. So instead of the conductivity, it's now the density. And we consider an interpolation profile zeta, so that zeta gamma indicates the conductivity, so the actual conductivity. And we can choose some sort of cubic or some other interpolation profile so that our conductivity, so the zeta gamma, remains admissible. So in very general terms, I won't detail this. The interpolation profile reduces the contribution of intermediate densities to the minimization of the objective. In other words, it penalizes intermediate densities and motivates that it takes either alpha or beta at a certain point. Now, we assume that this solves our first problem, and we go on to problem number 2. So why is our choice of descent direction not appropriate? So notice that J prime gamma lives in L2 and gamma lives in L infinity. After the descent step, where does the new conductivity live? It's not clear. It might not even remain admissible. And the second problem is that J prime gamma is too regular. L2 is not very regular. So how do we come up with a solution with this? So we consider a Hilbert space, which is continuously embedded in L infinity, so in the working space, and its inner product. And we choose to define the gradient as the unique element G in H, such that this equality is met for all K. In other words, it means we find the closest representative in H that best represents the gradient in the differential. Sorry. So with these two problems solved, how does one go about constructing a gradient algorithm to find the best design? So first you initialize, of course, gamma 0 to L infinity. You solve the state equation, so you find the U gamma, usually U gamma here, and you find the adjoint state, as we mentioned before. You infer a descent direction here. So here we have chosen this particular inner product. And well, you just choose some descent direction small enough so that it triggers a decrease in the objective function. And then you just project it on this set of admissible conductivities until convergence. So some numerical results we can see are appreciated here. So for example, or in all cases, the structure is kind of a tree. We have specified that F be uniformly on D, and the structures tend to branch out, sort of as to catch the heat. You can give that interpretation. And in particular, the observations that we have observed is that in all these figures, so if you have noticed, we vary the bounds. So the bounds are varied, the alpha and beta bounds that we mentioned earlier. And we noticed that the alpha bound, so the upper bound, controls the macro thickness. So how, at bigger scales, how thick the design will be. While the beta, which is the lower bound, controls the micro thickness. So at lower scales, how thin the design will be and how many microstructures we will tend to allow. So we also conducted some other numerical experiments, and we also varied the places where the absorbing boundary is. So in general, you might think of the insulating boundary as reflecting heat, and the structure will try and carry heat to the absorbing boundary. So that's the interpretation. That's the physical interpretation. And well, I would just like to say that we are able to, so these designs are physically meaningful. They have good interpretations, and it's all automated as by the algorithm. With this, we move on to the next section. And And in the previous, as in the previous section, we saw that typically we will want two-phased designs. So we will want a conductivity in one part and a conductivity in another part, so that it's hard. It's so the transition is hard. So there's no soft transition like the previous case. And now we seek to find the best geometry that minimizes the average sum of the mean temperature and the volume. So another example of this is, for example, take a heat sink, and how do you find the best geometry in materials that have different conductivity? So, for example, we have some aluminum here, I think it is, and copper here. So, some mathematical ingredients. How are the mathematical, again, what are the mathematical ingredients to solve a problem like this, to formulate a problem like this? Again, we've defined a set of admissible shapes, and just so it's clear, now we consider shapes. So we've defined the admissible shapes. So we take omega to be bounded and Lipschitz and compactly contained in some working domain D. And now we seek to solve more or less the same criterion. We seek to solve the mean temperature over D while penalizing the volume. And the variable in question is a set, a geometry, subject to this PD, this more or less the same PD, except that now the conductivity depends on the geometry that we find. So let us try and make these considerations more clear. So if we try and apply the same method that we did before, so we want to compute the Frechet differential or the derivative with respect to of the map J omega, we will have to define a proper notion of derivative with respect to the geometry. So how do we do that? Well, we consider this map. So identity plus some deformation field data that is essentially bounded with essentially bounded gradient. So that we express some deformed set omega theta by just the translation of the points. And as I said, we will call theta the deformation field. This is a visual illustration, so it's more clear. So we want to be able to stretch or compress the set, the geometry. And why do we consider this? Well, this notion of variation of shapes will naturally induce a notion of differentiability with respect to the domain. Because indeed, we can offload the differentiability to the map theta goes to the J of the deformed set. So definition, the mapping omega to J omega is said to be shape differentiable at omega if the mapping theta goes to J of the deformed set is differentiable at theta equals to 0. In expanding the definition of Frechet differential, we say that we want that there exists a continuous linear mapping L such that the following expansion holds. And we will call J prime defined by L the shape derivative of J at omega. Okay, so now we wish to compute the shape derivative of our functional that we defined. So how do we do this? Well, working on a moving domain is not very nice. So first, make a change of variables. So we have this. And now just apply the definition of shape derivative. Just calculate the Frechet differential with respect to theta and at 0. So for example, this is obviously this. And here we will have to apply some product rule so that we get two terms. And as you can see, this is the differential is exactly the same as here. So we will have it here. And this is just a theta equal to 0. So we will have U omega. So again, the problem is how do we characterize this term? Because it will be the differential of the map data goes to U omega theta, which is the solution to a PDE, only now that it's on the deformed set. And just for those that are more acquainted, yes, this is the Lagrangian derivative that we usually call this quantity, this term, the Lagrangian derivative. So how do we characterize this? Well, similarly as in the previous section, the complexity lies in this term. But I won't give a fully detailed analysis because similarly as before, we can just characterize it by a weak formulation. And the proof of differentiability is very, very similar. It's all just a few extra steps. You characterize it, the U bar, the perturbed scenario by a weak formulation, you apply the implicit theorem, etc., etc. And again, you will have that the shape derivative will implicitly depend on the deformation field theta. So you might think of theta as a direction. We may introduce an adjoint state, as we did in the previous section, to do away with this dependence. So it doesn't make sense to detail this all again, because it's more or less the same. And we shall fast forward. So we get the following theorem. The shape derivative reads like this. It's not very pretty or very natural, but the main idea is that we are able to get an expression of the shape derivative, so the derivative with respect to the domain, explicitly in terms of theta, where we have introduced a similar adjoint state as before. And again, we may apply the same Hilbertian extension regularization procedure to infer a descent direction. So for every theta, so for every direction in a continuously embedded Hilbert space in W1 infinity, we may find the closest representative of the closest field representative that will best approximate the gradient of the differential. So onto the numerics. So how do we evolve a domain, or how do we track a domain? This is it's not a vector space, so you can't just apply a descent step as before. You have to do something. You have to advect or track the motion of a domain. So for this, a typically used method is to use the level set method. So I won't detail it here, but see the book by Sethi and James. And you consider a level set function, so a function which has negative subdomain. So it has negative subdomain omega, and its zero level set is its boundary. And you consider, or you are able to derive the following also partial differential equation for the level set function.
Carlos?
Yes.
Sorry to interrupt you. It's just to inform you that you have about 2 minutes left.
Okay. Yeah, sorry. I have. No so problem. The descent step is now an advection step. So fast forwarding again, the descent step corresponds to solving this advection equation. And some observations, contrary to the previous section, now area occupation is preferred to micro branches. So now you don't see as many micro branches. And the Dirichlet boundary still determines how the optimal design will look like. So for example, the designs tend to go outwards towards to catch the heat, to conduct back the heat to the absorbent boundary. And just to give more or less of a conclusion, where you can go, where to go from this? Well, of course, we have seen 2D designs, and now we would like to extend to the 3D case. We can also consider some other states, so the linear elasticity, so a more mechanical model, and other functionals. So you can minimize the compliance, which amounts to minimizing the energy dissipated inside the structure. So for further references on the topic, if you're interested, I will recommend Allaire's book, Conception optimale des structures, that is in French, Shape Variation and Optimization by Antoine Anro, and Introduction to Shape Optimization. And finally, the very excellent review paper by also Allaire and Dapogny and Juve, Shape and Topology Optimization. And with that, I have finished my talk.
Thank you very much, Carlos, for this very exhaustive talk. It was really interesting to discover that topic. Are there any questions from the audience?
Yes, I have a question.
Thank you.
So I have actually two questions. So the first one is this unphysical continuous changing of the coefficient. But I don't see why it's unphysical. I mean, you can just have for instance, two different metals, and you can mix them in different proportions, which change continuously. So this would give you such a material.
Yes, but I think if you mix them, you will still have you won't have a. So, for example, in the numerical result we saw, you won't have a conductivity which is very high here, and then very low, and it's continuous all along this path.
Okay,
so yes.
The other question was, okay, this gives you different designs. And is it planned, or did you have made experiments with physical devices?
No, I have not made physical experiments with physical devices. It's simulated, yes.
Okay, simulated. Okay, because also for these tree-like structures, it's difficult to imagine how to build them. I mean,
yes, I think you could. So for example, if we were taking in 2D, and this is the domain, here would go the metal, which dissipates the greatest amount of heat, and maybe we will have some sort of device or cooling here that carries away the heat. It's not that physical since it's in 2D, so a more physical setup would be to consider the 3D case and have some absorbing or Newman boundary conditions that carry away the heat. So like in the microchip cooling example. But I still think it could be physical. I would expect that you get some sort of graph, or not graph, some sort of tree structure that tells you have to add a lot of conductivity here, where the Dirichlet region is, or the yes.
Okay. Yeah. Thanks.
Okay, I also have very high-level questions. If other people don't mind, then we will not be taking so much time so as to be fair between all the presentations. My very high-level question, Carlos, is would it be realistic or interesting to consider a sort of dynamical setup where your constraints can change over time? So that, for example, you have your coefficients alpha and beta, which would depend on time, and where you would solve this shape optimization in a setup where you, I don't know, I'm like just imagining setups where your constraints will change. Is this setup existing already or not?
Well, the alpha and beta are more or less just the bounds that control the conductivity. So those are, at the end of the day, the bounds that you can impose, your manufacturing constraints.
Okay.
So I don't think the conductivity would be changing.
Sorry, so yeah, this is about the material then, right? Not the external environment, those alpha and beta.
it's more or less, yes, it's about the manufacturing constraints. How, as you can, if you want to think of it like this, it's about the height of the, it's how big you can allow the conductivity at one place and how low you can allow it.
Okay.
But it won't be changing over time. You could allow for differential conductivity, so that would be a smoother changes in conductivity.
Okay then. Okay, thank you. So for your presentation, Carlos. I hope everyone learned a lot of stuff. Personally, I learned some new stuff, so I'm happy. So I think our session this afternoon is finished. And this is also the end of this workshop from Anatoly. So if other people have anything else to say.
Thank you very much. I guess this is a good idea to change presentations and topics of research. For MIPT, it is after defenses of bachelor and master students. And in your case, I guess it is just before the defenses. Am I right?
Yeah.
Yeah, so there is no big deal to have, for a student to have almost ready to go or ready to go presentations. It goes for free. So it is the great idea to make this workshop for young researcher. Anatoly, thank you very much. Anatoly, did you hear me? No, okay. Anyway, Anatoly, Masi, thank you.
Thank you, Anatoly, and thank you, Vadim. Thank you so much.
Okay, so all 4 sessions are recorded. So links are available. Thank you.
I also create a playlist of all 4 workshops from one link in YouTube.
Ah, great. We'll send you these links.
All right.
So have a nice day.
Have a nice day, everybody.
Bye-bye.
Thank you so much.
Bye.
For the presentation. See you.
Thank you. Bye.